It's the question that always comes up when thinking about the origin of the universe. What came before the Big Bang? And if there was no before, what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including a young Albert Einstein, assumed the universe itself to be eternal and everlasting. Of course, stars could be born and die, planets could collide, and civilizations could arise and fall, but on large spatial scales and over long periods of time, it always looked roughly the same as it does now. Only in the 1930s did convincing evidence of the expansion of the universe appear, and in the 1960s, evidence of its origin in the Big Bang. Such a radical revolution in the scientific worldview has not occurred, perhaps since the recognition of the heliocentric system. But then, two equally difficult questions arose. First, what actually was before the Big Bang? What was space like before it began to expand, and how long did it stay in this primordial state? Secondly, everything that has a beginning has an end, so what will it be like, the end of our universe? The English physicist Brian Cox set out to find an answer to this question, and now, in a world-shattering revelation, physicist and professor of particle physics Brian Cox has just declared that he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head. We used to think that the universe emerged in that state, very hot and very dense, at the beginning of time, and we used to call it the Big Bang. But now, we strongly suspect that the universe existed before that, and in that sense, it's possible to speak of a time before the Big Bang. Join us as we dig deep into how Brian Cox just debunked the Big Bang. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to everyone, regularly contributing to public debate and discussion. Never one to shy away from the big questions, the physicist previously took on the story of the Big Bang. The idea of the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding. Today, and if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on. It also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, that means the universe cools as we age, and hence, things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart, a time where matter and antimatter pairs could spontaneously form as the universe was so energetic that pairs of particles and antiparticles could spontaneously be created, a time where individual protons and neutrons break down into a quark-gluon plasma, as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus, and finally, a time where the density and temperature rise to infinite values, as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity that represents where the laws of physics break down, also is understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark-gluon plasmas in the lab, we've created matter-antimatter pairs, we've done the calculations for which light elements should form and in what abundances during the early stages of the universe, made the measurements and found that they match with the Big Bang's predictions. Coming forward even farther, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner. Except, that is, in a few regards. 3 specific things you would expect from the Big Bang didn't happen. First off, the horizon problem. If we look in different directions, we see the universe as having the same temperature and density everywhere, but even since the start of the hot Big Bang, these regions never had time to communicate, exchange information, or reach thermal equilibrium with one another. So how did they evolve to reach the same temperature and conditions everywhere? Next, the flatness problem. In an expanding universe, in general, there's a fight between the initial expansion rate that drives things apart and the gravitational effects that work to bring everything back together. In our universe, we observe that these two opposing forces are pretty much perfectly exactly balanced, leading to an exactly spatially flat universe. So why was our universe born with those properties? And last, the monopole problem. If the universe reached these arbitrarily high temperature and energy conditions, then why are there no exotic leftover heavy relics, right-handed neutrinos, magnetic monopoles, and other particles that should be observable and left over today? We can always shrug our shoulders and mutter something like, those must have just been the initial conditions or the way the universe was born, but that runs counter to the enterprise of science. Instead, we look for a mechanism that would mandate and set up these conditions. That mechanism sprung forth in 1980 in a remarkable paper by Alan Guth, who noted explicitly that an early, rapid, and relentless phase of exponential expansion, where the universe's energy was not distributed among matter and radiation quanta, but rather was inherent to the fabric of space itself, would solve all 3 of these problems. But because inflation represents an exponential expansion of space, rather than one that terminates in a singularity like the original model for the Big Bang, it sets up a very different picture of the beginning of a whoosh that led to a Big Bang, rather than the emergence of time and space from a singular state. Now, we get to address the really big questions. What does all of this mean for the true beginning of the universe, if such a thing even existed? Well, the bottom line might be the hot Big Bang definitely happened, but doesn't extend to go all the way back to an arbitrarily hot and dense state. Instead, the very early universe underwent a period of time where all of the energy that would go into the matter and radiation present today was instead bound up in the fabric of space itself. That period, known as cosmic inflation, came to an end and gave rise to the hot Big Bang but never created an arbitrarily hot, dense state, nor did it create a singularity. What happened prior to inflation, or whether inflation was eternal to the past, is still an open question. But one thing is for certain, the Big Bang is not the beginning of the universe. But if the Big Bang wasn't the beginning, what was it? What happened before the Big Bang? Short answer, we don't know. Long answer, it could have been a lot of things, each mind-bending in its own way. It's possible that before the Big Bang, the universe was an infinite stretch of ultra-hot, dense material persisting in a steady state until, for some reason, the Big Bang occurred. This extra-dense universe may have been governed by quantum mechanics, the physics of the extremely small scale. The Big Bang then would have represented the moment that classical physics took over as the major driver of the universe's evolution. For Stephen Hawking, this moment was all that mattered. Before the Big Bang, he said, events are unmeasurable and thus undefined. Hawking called this the no-boundary proposal, in which time and space are finite, but they don't have any boundaries or starting or ending points, the same way that the planet Earth is finite but has no edge. Or perhaps there was something else before the Big Bang that's worth pondering. A bold idea of Professor Brian Cox suggested there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series A Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation. Flipping the Bible creation story on its head, Brian Cox proceeded to explain the science creation story, and the crux of the story is an unimaginably violent expansion, which, in a billionth of a billionth of a billionth of a second, transformed this microscopic patch of energy into an expanding ball of gas over 10 billion kilometers across. This titanic event created what we now call the Big Bang. The question of what happened before the Big Bang is one of the most profound in cosmology, challenging both our understanding of physics and the limits of human imagination. For centuries, the prevailing belief was that a divine being created the universe, a view held even by the eminent scientist Isaac Newton. This notion of a universe with a definitive beginning dominated until the early 20th century, when the Big Bang theory emerged. The Big Bang theory was born out of the observation that distant galaxies are receding from us, implying that the universe is expanding. This expansion suggested that the universe was once much smaller, denser, and hotter. The discovery of the cosmic microwave background radiation in 1964 provided compelling evidence that the universe began from a hot, dense state about 13.8 billion years ago. However, the Big Bang theory raises several questions that it cannot answer on its own. For instance, the horizon problem points out that different regions of the universe appear to have the same temperature, even though they should not have had enough time to exchange heat and reach equilibrium. The flatness problem queries why the universe is so precisely balanced between continued expansion and gravitational collapse. Lastly, the monopole problem asks why we do not observe certain heavy particles that should have been produced in abundance during the early moments of the universe. In the 1980s, a groundbreaking concept known as cosmic inflation was proposed by physicist Alan Guth. Inflation theory posits that the universe underwent a rapid exponential expansion in the first fraction of a second after the Big Bang. This expansion would solve the horizon, flatness, and monopole problems by stretching the universe so rapidly that any initial irregularities would be smoothed out, leading to the homogeneous and isotropic cosmos we observe today. But inflation raises its own questions. If inflation is true, what caused it, and what happened before it? Some theorists, like physicist Brian Cox, suggest that the universe may have existed in a different form before the Big Bang. One hypothesis is that the pre-Big Bang universe was an infinite, stable, and ultradense state governed by quantum mechanics. Another intriguing idea is that our universe is just one of many in a larger multiverse, with Big Bangs occurring in different regions independently. Stephen Hawking offered another perspective with his no-boundary proposal. He suggested that time, as we understand it, did not exist before the Big Bang. In this view, asking what happened before the Big Bang is akin to asking what is north of the North Pole. It is a nonsensical question, because there is no such thing as E before G in a temporal sense. According to Hawking, the universe is finite but unbounded, similar to the surface of the Earth. Brian Cox's own contributions to this discussion involve a concept where, before the Big Bang, there was no matter, only an ocean of energy and spacetime. This nearly still ocean would occasionally ripple, causing violent expansions known as inflation. These inflations could create multiple universes in a multiverse scenario, where each universe begins with its own Big Bang. While these ideas are speculative and remain topics of intense debate and research, they underscore the limits of our current understanding. The true nature of the universe's origin is still one of the greatest mysteries in science. Advances in observational technology and theoretical physics may one day provide clearer answers, but for now, the question of what happened before the Big Bang remains one of the most profound enigmas in cosmology.